Good evening, everybody. My name's Stephen Peats. I'm Chair for Home Counties South East. And just before I introduce our presenter this evening, I've just got a couple of announcements to make. First of all, thank you for taking the time to attend this evening. And thank you to Ella from the Region's Executive of Banham, providing all the much needed technical support for the meeting to go ahead. And really, it's just a reminder from everyone who's attending this evening that the regions are in place to support the charitable objectives of the institution and encourage intellectual welfare of members and improve the understanding of building services engineers amongst other professions as well in society in general. And this is carried out by organising periodic meetings and other activities related to the theme of the built environment. So if you've got ideas for future meetings or other activities, I'll just drop my details in the message box and please contact me. So just a couple of housekeeping points. If you could have your cameras turned off and your audio on mute, this will help transmission. And if you have any questions, please put them in the chat box at the end of the presentation. I'll read the questions to the speaker and ask the speaker to respond. So welcome tonight, Barrie Welsh of Hamworthy Heating. And the seminar is on new boilers and old heating system hydraulic design. So over to you, and thank you for this evening's presentation, Barrie.
Pleasure. Thanks for the intro. Hello, everybody. Thanks for attending. My name's Barrie Welsh. I work for Hamworthy Heating. I'm the technical sales manager, which is a very posh title. What I basically am, though, is how long have I been doing it now? About 35 years. Time-served industrial gas engineer. So these days I work for Hamworthy. I advise our sales team technically. I work with R&D, product management. I go out on site, I troubleshoot, I work with consultants, I work on design and things like that. I don't know everything. Please don't assume that I do. One rule of mine when I'm presenting a CPD is please ask a question. There's no such thing as a silly question. Everything's relevant. Use the chat thing. We'll read them out, and I think it's anonymous or fairly anonymous. I can't promise I'll have the answer. If I don't have the answer, I will find it for you, though, eventually. So that's me. This is the company. We're Hamworthy, British Engineering Excellence. We're a British commercial boiler manufacturer. We design, we test, we manufacture, and we source market-leading heating products and hot water products. So we provide energy-efficient commercial heating, hot water, and renewable solutions to buildings all the way across the UK. Everybody's got history. We like to think we got some heritage, and we go all the way back to 1914. There was a couple of brothers in Poole, and they set up Hamworthy Engineering. And there is probably hundreds of years of experience in Hamworthy going into all our design and boilers and heat pumps and things like that. Since 2008, we've been part of Group Atlantic, which is one of the world's largest privately owned companies, owned by two very pleasant French brothers, which kind of fit in nicely with the brothers that started Hamworthy, I suppose. And we're part of their UK division now. That's Group Atlantic UK, Republic of Ireland, North America. So what are we going to learn? So part one is establishing the existing system and comparing open and closed heating systems. Part two, we're going to have a look at primary circuit design and how we're going to connect our nice shiny, hopefully Hamworthy boilers to the secondary circuit. So we're going to look at low loss headers, plate heat exchangers, no flow boilers, and buffer vessels. And what will you get apart from a headache? You're going to get a learning outcome sheet, a CPD certificate, a sizing guide that comes from our marketing people, and a feedback and event evaluation form. So you can tell us if we're good or if we're rubbish. If we're rubbish, it gives us a chance to improve, doesn't it? So part one, establishing the existing system. Here's a couple of lovely old things here. I've no idea what these boilers are. Sorry, I'm just going to find my laser pointer. There we go. Absolutely no idea what these things are. For anybody not experienced in this, all this stuff around here, all around the boilers and all around the pipe and everything, is asbestos lagging. which was an absolutely fabulous product. You could do so much with the specials. The downside of it, unfortunately, had this tendency of killing everybody that worked with it. So if you're going to take out old boilers and you put new boilers on, it's very, very important to establish what is the existing type of system. Some old systems, not so much these days, but they're still out there. They were called open vented systems. So what are they and how do they work? So here's our Hamworthy Pure Well boilers here. We've got 3 boilers in the cascade. Group of boilers is called a cascade, bit like a murder of crows or an embarrassment of pandas. Someone told me the other day, I thought it was quite a good one. I digress. So we have our 3 boilers here, and we have our primary circuit, low loss header. Over here we've got our heating load, DHW and heating, and up here, up in the on the roof or in the roof, as high as you can possibly get it, really, is our F&E tank, our feed and expansion tank, or cistern as it's sometimes called. To get water in the system, mains water comes in via a ball valve, exactly the same type of thing that's in your loo, really. Fills up the tank, comes down the coal feed pipe into the system, fills the system up. Obviously the system is going to fill to the same height as the water level, and then the other very important part of the system is the open vent. That rises up above the F&E tank, hangs over. It's got an open-ended pipe. Obviously the water level will be exactly the same as the top of the system. Obviously water, when you warm it up, it expands. So what happens, you get a bit of expansion coming up this vent, sometimes up the coal feed as well if you haven't got a check valve on it. The water level in the tank rises a little bit, but shouldn't rise too much. One downside of this, if you get the coal feed and the open vent too close together, you can end up with a situation called what we call pumping over. And what happens is the primary pump will push water up the open vent into the tank. It's then drawn back down into the system via the F&E tank. And what that does, that introduces oxygen into the water. Oxygen is the enemy of the heating system, really. If there's lots of oxygen in the system, you get oxidization, and that basically introduces the rusting process, and then you get all the other horrible stuff like hydrogen gas and ferrite sludge and things like that. Modern boilers, I'm going to say this a lot, modern boilers do not like dirty water. So it's very, very important that systems kept clean and the coal feed and the open vent are correctly spaced. So that's open vented. So what are the downsides for open vented systems? Well, they're generally used in older systems. You can't reach high pressure, so if you know your pressure is entirely dependent on your head pressure or how high the tank is above the system. You get all sorts of stuff entering the water. They generally start off with lagging jackets and lids, and over the years the lids get lost and you get dead pigeons and all sorts of horrible stuff in the water which gets in your system. As we've already discussed, you can end up with oxygen in the system and the system will oxidize and rust. You need to think about where the feed and expansion tank is going to be. Like I say, often as not, it's on a roof or it's in a roof. Health and safety implications now are going on roofs or getting ladders out and things like that are quite time consuming, and you need to think about, you've got some clumsy oaf like me clamping about in his size 10 steel toe cap boots, putting feet through ceilings and falling off roofs. And you need to think about your pipework run and how you're going to stop it from freezing and losing heat. Did you know many boiler manufacturers now specify sealed systems? We've got some of our boilers that will still run open vents, the ones with the smaller water I was trying to thought now, the smaller water quantity boilers often now run on a sealed system. So let's have a look at sealed systems, or closed or pressurized systems. So here we've got 3 Hamworthy Stratton boilers, wall hung boilers these are. Here's our primary circuit. We've got individual primary shunt pumps, low loss header, and the same heating load, DHW and heating on this side. So instead of the F&E tank up in the roof, what we've replaced that with now is we have a coal mains water coming in. So instead of connecting to a ball valve, it connects to the pressurization unit and also to a thing called a quick fill. You can't fill a heating system from a pressurization unit. The water volume is too great. It's not designed to do that. You'll burn the pump out probably. So we use a quick fill, which is like a commercial version of a filling loop that most people have on their combi boilers and things like that at home. And what that does, that forms a break between the heating water and the mains water, so the heating water can never ever make its way back into the mains potable water system. So we fill the system up to whatever required pressure off the mains, and then the pressurization unit takes it to that last bit and maintains pressure. Now, instead of the open vent hanging over the tank, we've now got an expansion vessel. An expansion vessel is basically one of a better expression, it's just a tank. It's just a sealed vessel. Where the water goes in, it hits a neoprene diaphragm. And then on the other side of the diaphragm is an air charge. The air charge goes in via something called a Schrader valve. You all know what a Schrader valve is, even if you've never heard it called this name before. And it's exactly the same thing as the way you pump your car tires up. That's a Schrader valve. And you either pressurize it with dry air or nitrogen. As this system expands, what happens is the expanding water pushes against that neoprene bladder, and it rises upwards, and it's cushioned against the air or the nitrogen charge, and that's how it accounts for expansion and well, not contraction, but expansion of the water as you heat it up. All very straightforward stuff, really. This is showing an anti-gravity loop as well, and all an anti-gravity loop is, it just keeps elevated temperatures off the neoprene bladder, and it helps to prolong the life of that thing. So the benefits of a closed and a pressurized system is system cleanliness. Modern boilers don't like dirty water. It won't allow any oxygenated water into the system, and it's much easier to keep that water clean. Space and access. Generally, most of the kit is going to be located in the plant room, so you haven't got anybody like me tramping about and falling through ceilings and things, getting ladders out and making a nuisance of myself. A lot of modern pressurization units, you can monitor system pressure. So you can have alarm interlocks. It can obviously interlock to the boilers if the pressure is getting low, if there's been a leak, or it can be interlocked to BMS, which can obviously then send out remote alarms and things like that to engineers or people monitoring the system. And it can also, very importantly, monitor water volume. So if you've got a system that's leaking, it's not a lot of good if the pressurization unit just keeps injecting water into it. We call that raw water. Mains water is raw water. If you're leaking, what's going to happen is, even if you put inhibitor chemicals into the system and treated it nicely, that raw water is going to dilute your chemical that's in the system, and you're also introducing oxygen, so you've got a two-pronged attack on the system. Your chemical level is being diluted and your oxygen level inside the system is going up, and it will start to oxidize and rust and corrode. And as I said, many manufacturers now recommend or insist the use of a sealed system. And as I said earlier, you get a dry roof space, you've got no one like me making a nuisance of himself. And it's a European requirement as well. So if you go fitting boilers in Europe, you can't have an open vented system. So part one, we've looked at establishing the existing system. What are open and closed heating systems? So part two is all about primary circuit design and how we're going to connect our hopefully nice shiny Hamworthy boilers to your existing system. So a couple of questions there. Is the pipework suitable? Is it big enough? Can it handle the flow rate? Is it leaking? Is it corroding? Does it need any maintenance? Are you moving from atmospheric to condensing? If you're using premix boilers, almost certainly the answer to that question is going to be yes. One of the considerations with atmospheric to condensing boilers is the flue is almost certainly going to be unsuitable for condensing boilers, A, because of the acidic condensate, and also because the sizing regime is different. One of the advantages with condensing boilers, as often as not, is the flue's a lot smaller. So using some of these flue specialist companies that are around, they can often line the flue with like a resin liner. So you use the old flue as a liner, and it cuts down the cost. It saves having to replace the whole flue for brand new. You need to think about your pump considerations. All boilers, apart from one that we will talk about in a minute, but all boilers need to have a constant flow rate. It's a bit of a misnomer going around in the industry at the moment that you can force modulate boilers by adjusting the flow rate, and you can't do that. Boilers don't like it. It's not how they're designed to operate. So the pump needs to match the manufacturer's minimum flow rate for the delta T that you want to run it at. And you need to think about protection. Modern boilers they don't like dirty water, Mr. Mannering. So you need to think about how you're going to put the chemicals, how you're going to dose the system. Generally, we use dosing pots, don't we? Normally pipe between flow and return, so you get a good flow through it. You can use air and dirt separators, strainers, and there's a whole host of technology on the market now. You know, we've got mag filters, magnetic filters, there are side stream filters, Alsator systems, all sorts of things out there to keep systems clean. One of the main problems that we come across with our boilers failing prematurely is dirty water. We know, we design, we test these things to absolute destruction. If they're connected to a nice clean water system with no oxygen in the water, they will last for decades. If you connect especially aluminium boilers to a system that's got lots of ferrite and copper and oxygen in the system, it doesn't matter if it's our boilers or any other manufacturer, they will fail prematurely, and you know, you've ruined your expenditure. So circuit design, minimum flow rate. Does the flow rate of the current pipe work match the primary shunt pump details? In other words, can we get this water going fast enough for the boiler? If not, what are you going to do? Well, this is what happens, you see. If you've got dirty water with ferrite and scale in it, and your flow rate is too slow, this makes the problem even worse, because what happens is the stuff gets circulated, the rubbish gets circulated in the water stream, it hits the boiler tubes, or the waterways through aluminium boilers and things like that, and it's hot. What happens is it sticks to the inside of the boiler and it builds up like this, and instead of having this 100% water, you've now got 50%. And what happens is the boilers start to kettle, they get noisy, they become very inefficient, and this will eventually fail the boiler, because what will happen is you'll end up with a big hot spot on the bottom of this tube, which will fail and it will start to leak and it will write your investment off. So what can happen? You can damage the boiler's heat cell or heat exchanger. It'll scale up. It takes much longer to heat up, and you will drastically reduce the life expectancy of that boiler. So how are we going to connect? Now we've got the pumping arrangement sorted out. Let's have a think about how we're going to connect to the secondary circuit. What are the choices? So this section looks at the dark art of the low loss header, which in reality is very straightforward bit of kit. So it's also referred to as a common header or a balanced header or low loss flow header. Now what this does, it provides better flow of primary and secondary circuits. As I say, boilers like to have to have a constant flow rate, so that's great. So we get a constant flow rate going around on our primary side. However, if you size your header correctly on your secondary side of your system, you can adjust that flow rate according to system demand. All this is just a hollow pipe. We've got 4 tappings on it: primary flow, primary return, secondary flow, and secondary return. When the system's dead cold, generally what happens is that it mainly short circuits. So these secondary pumps will be going at ramping up to their maximum rate. So what's going to happen? The hot water is going to pretty much go flow to flow around the system. It's going to come back. You're going to get a little bit of mixing going on in the header. A lot of it, if it's cold, it's going to come back into the primary return through the boilers, reheated back into the header. As the system's starting to warm up, especially if you're using an inverter driven variable speed drive secondary pumps, the pump speed will start to slow down as the temperature increases. And what happens is, as this water's coming back, we end up with plenty of mixing going on inside this header, provided it's sized correctly. So a lot of this is now going to mix with this primary circuit, and it's going to come straight back into the secondary circuit. And some of this is going to come back down this way into the primary return. What that's going to do, the boilers are going to pick that up. It's going to lift the return temperature. The boilers will see that on their thermistor, and they will then modulate the burner rate downwards and use less energy. It allows the boilers to operate at a constant flow rate, while flow rates and temperatures may vary in the secondary circuit. I should say, as well as modern boilers not liking dirty water, modern boilers don't like variable flow rates. A quick schematic just to explain on a header. This is one of our Stratton boilers. So this is what we would call our primary circuit. Here's our header in the middle, and this would be our secondary circuit. And this is showing this optional kit we do. You can bolt a manifold on to have various different ports coming off of it. Automatic air vent on the top. Air will always go to the highest point of a system, so when you're filling the system, the air is always going to go up there, and that will let it out. And then you've got a drain on the bottom, often as not used as referred to as a sludge cock by us older engineers, because we're used to this being full up with junk. What happens with a lot of guns is it hits the header, because the header is the neutral point of the system. Both of the circuits lose their pump velocity as they hit the header, so a lot of the time the sediment and ferrite and stuff ends up sort of settling in the bottom of the header, and it helps prevent it going back into the boilers. But modern boilers don't like dirty water, so hopefully your system's going to be kept nice and clean. And this is where it goes. So we know all about this: expansion vessel, pressurization unit stuff, 3 boilers in the cascade. Is our primary circuit. Here's our low loss header. The primary circuit is, in this case, is circulated with individual boiler shunt pumps, and then we've got a single. There we have. Sorry, we've got 2 primary, secondary pumps coming off this low loss header. So these pumps will be set to a fixed speed. These pumps can be variable according to system load. So which type of header? There's 2 types. There's a vertical type. That's generally what we use because it's much easier to get the air out of the thing. And you can have horizontal ones as well. You generally only really use those if you're forced to with space constraints, really. A lot of modern ones now, they've got combined air and dirt separators. The best way to describe that is if you cut it open, it looks like it's full up with chimney sweep brushes. That helps to keep some of the system debris out of the boilers if the system's a bit grubby, but hopefully we would have dealt with that. Stratton Mark 1s. Here's our primary circuit with a low loss header here. These boilers have got integral pumps built into the actual primary pumps are inside the case here. You can't see them. And here's our secondary pump over here on the, I think that's on the return looking at it. Looks like it creeps around the back of the flow. Maybe not, maybe it is on the flow actually. So secondary flows coming out of here, dropping down here through the pumps around the system. These can be variable speed, these pumps, and the return comes back into the bottom of the low loss header here, where we're going to hopefully get a bit of mixing going on. Looks like there's temperature gauge on top of that one as well. Upside of it, protects the boilers, ensures adequate flow on primary circuit. Modern boilers do not like variable speeds. Variable flow rates rather. Sludge collects as a result of low flow velocity, but obviously there's going to be no sludge in your system now because I keep telling you, modern boilers don't like dirty water. Package can often be supplied by the manufacturer to match the boiler connections. We do pipework kits for pretty much all our boilers, and a lot of those we can also supply a flow header with them. Downside is if you're converting, obviously you've got the cost, you've got additional cost for the pumps, additional pumps, and the header itself, you know, insulation, all that sort of stuff. You need a bit more space, and you need to think about the number of ports. You can often buy a 4-port flow header off the shelf. If you want more than 4 ports, then often it's a bespoke made thing. It's very important they're accurately sized. It doesn't really matter if they're oversized, because it gets to a certain point, if you dramatically oversize your header, it just becomes a buffer. But if you undersize a header, that's when it all falls over. There's not any point in having a header, because all it will do, it will short circuit. It will literally just go flow to flow, return to return. You won't get any mixing going on in the middle, and there's not really much point in having it. So sizing considerations, correct sizing, correct design and sizing, and where you're going to put it obviously is important. You can refer to Hamworthy sizing chart. You can refer to the CIBSE guide B&H. And just a quick question, what if the temperature differential is different on the primary and the secondary circuits? Good question. It's not a problem. As long as the header's sized correctly, you can have different delta T's. So quick rule of thumb, the higher the output of the boiler, the larger the header diameter is, and the longer that makes the header. The larger the system design temperature drop and the lower the flow rate, the smaller the header diameter, and obviously the shorter it is. When you look at our sizing chart, strangely enough, it doesn't give you a length. All it gives you is a diameter. And what you do, the rule of thumb is if you multiply that diameter by 4, that gives you your minimum separation distance between primary flow and primary return. So if the sizing guide comes up with a 100mm diameter header, as long as your primary flow and return connections are a minimum of 400mm apart, that header will work beautifully. Doesn't matter if they're bigger, but when they're smaller, it can slow the header mixing up. So just a quick rule of thumb. So a 0.5 megawatt boiler at a 30-degree delta T, that needs, well, there we go, 100mm diameter low loss header, and we already know that needs a 400mm separation between flow and return. So low loss header consideration, primary pumps. How are we going to circulate that primary circuit? Well, does the boiler have an integral pump like the picture? If it does, job done then. Don't need to think about anything else. If not, what size pump do you need? Best thing to do is contact the pump manufacturers. We make boilers, they make pumps. We use Wilo pumps on most of our kit, but there's obviously other manufacturers out there, Grundfos and Loire and people like that. They've all got very good technical departments. If you tell them what you're doing, they'll spec you a nice pump. Where are you going to put it? Primary circuit pump or individual boiler shunt pumps? I often get asked this question, is there a right or wrong way of doing this? And there's not. There's no right or wrong way of doing that. As long as you're maintaining minimum flow rate through the boilers, it doesn't matter if you have one pump or multiple pumps. Where it really comes down to is system design and value engineering. So I think if you have an office block, nothing particularly critical, that if the heating system fell over due to pump failure in the afternoon, which is fairly unusual, people can put a jumper on, or people can go and work from home. No one's going to die, no one's going to suffer ill effects particularly. However, if you've got something like a nursing home or a hospital or a building with vulnerable people in it, I think really you want to be looking at individual boiler shunt pumps, because that obviously designs much more redundancy and resilience into that system. Obviously primary circuit pumps, you can use twin-headed pumps, which can negate this a little bit, but obviously if the impeller fails on that pump, then the whole site falls over, doesn't it? So here's the back of some of our Hamworthy Wessex boilers. You can't really see the boilers. See the back of the pipe kits, and we've got individual shunt pumps on these boilers. So this is a system that's going to be nice and resilient. Obviously, if this pump falls over, we've still got the other stuff to fall back on. So primary circuit pump. Pros and cons. You can have a dual shunt pump, as we said, for option for backup. It's cheaper to install. The downside is you need a larger electrical load for that pump, so it's probably going to be 3-phase. Size of the pump is large. Often it needs more than one person to install it and remove it for maintenance and things like that. It does build in a single point of failure onto a system, and you've also got potential heat losses through non-firing boilers. Generally the way now with boilers is the modular system, which Hamworthy conceived in the 70s. Obviously there are ways of controlling our boilers in unison and things like that, where we try and keep most of them running at a low modulation rate, so negate that heat loss through the boilers. But obviously if you've got a large turn down ratio on, say, district schemes and things like that, you might want to look at maybe 2-port motorized valves or things like that on the back of these boilers if you're going to use a single circuit pump. So if you're going to use individual boiler shunt pumps, what are the pros and cons? So you get a better water circulation through the boiler. You don't have to worry about the reverse return configuration. Smaller electrical load, often as not they're single phase. The pumps can often be connected and controlled by the boilers. You get a better master system. The downside really is there's more pumps to purchase. As I say, no right or wrong way of doing that. It really is what best suits the building. So let's have a look at the dark art of something that sounds very complicated, reverse return, and it's when it's explained, it's very straightforward thing. I'm just going to move that. There we go. So if you're going to use a single pump, a single primary pump on your primary circuit, let's say we put it here where this arrow is on the primary return, pushing through the boilers. It's always a better way of doing it, push through the boilers rather than pull, but you can do it the other way around. it seems to work better on the return. Now then, if we connect that return straight into boiler number 4 and then sequentially into 3, 2 and 1, what's going to happen is water's lazy. It will always go the easiest route. So most of that flow is really going to go around boiler 4 back into the header. We're going to get some through 3, bit round 2, probably hardly anything round 1. Boiler 4 is going to do most of that work. So what we do to negate this, we install a reverse return. The way I prompt people to remember this is the gas engineer way of first in, last out. So, or first out, last in, if you like. So water's leaving boiler number 4, first one on the flow into the low loss header. The return comes back. Instead of coming into boiler number 4, we bring that all the way back to boiler number 1, which then gets the return first. And what that does, that hydraulically balances that flow and return across that cascade of boilers, and we get equal flow across the entire cascade. So why use it? Stop short cycling within one boiler. It gives extended life to the, that boiler and the entire cascade. It's all going to wear individually if you're controlling it properly. And some manufacturers got this built in as standard. All of our pipe work kits are configured reverse return as standard, so you don't have to think about it. So that was low loss headers. And let's have a look at plate heat exchangers. As a boiler manufacturer, I love plate heat exchangers. They're brilliant. They protect our boilers from dirty water, because modern boilers don't like dirty water, do they? Consultants don't like plate heat exchangers, and for the pure reason is you lose a bit of heat over them. I think losing a bit of heat and a bit of efficiency is better than writing off some very expensive heat exchangers. That's just my opinion, though. So a plate heat exchanger will provide complete total hydraulic separation of the primary and secondary circuits. The main reason I like them is it protects new boilers from dirt and debris from existing secondary circuits. Obviously, it's going to make your investment last a lot longer. Your client's going to be a lot happier with it. So which type? There's brazed. You can't take those to bits. They're generally only a brazed plate heat exchanger have some very light commercial applications, but generally they're on things like combi boilers and heat pumps and stuff like that. You can't take them apart. When they get clogged and blocked, you just throw them away. The gasketed type is generally what we see on larger commercial stuff. You can take them to bits, you can clean it out and put the system back into service again. And you can obviously, you can extend the capacity of this as long as your frame is big enough. We call them curtain plates. Here's an example of one here. So when this is in operation, obviously all this is bolted up tight. Here's our plates here. And, on the secondary side, the water might be dirty. So what we're going to do is we're going to monitor the delta across the secondary. As that delta is changing, we know this plate is starting to get blocked. Now, what we can do is turn off all 4 valves, take the system offline for a couple of hours, undo the bolts, everything slides forwards like a curtain rail. We can hose or wash all these things off, clean them off, replace the neoprene gaskets and bolt it all back together, vent the air out of it, put it all back into service. Decent engineers should have that up and going in a couple of hours. Probably take me these days about 5 hours, I would imagine. But that is a plate heat exchanger, and obviously if your rail is big enough, you have the capacity to increase your output on the plate. So quite an interesting schematic of a plate heat exchanger. Now, here we go. We've got our pressurization stuff here. We've got 3, they're either Wessex or Upton boilers here. 3 boilers and a cascade. Primary circuit, plate heat exchanger where the low loss header will be. Single primary pump on the circuit. And we've got a secondary circuit here. However, we've got something interesting up on the top here. We've got our old mate, the F&E tank. Now, at the start of this, I said F&E tanks are not the greatest thing in the world. If you can, you should move to a pressurized system. However, this could be it could be the London History Museum, or it could be a beautiful place of worship, or it could be an old stately home or anything like that. This could be a 50-year-old iron system with iron radiators running at a fairly low pressure, because it's only on dependent on where that F&E tank is. It's a very, very brave engineer that wants to pressurize this and create leaks and things like that. So generally in that scenario, as engineers, we just like to let sleeping dogs lie. We know it works. It's always worked on open vent. We'll try and clean it up as much as we can, but basically we're going to let that to its own devices and not try and induce any problems into the system. We split that with a plate heat exchanger. This can get on with it. You're never going to clean this system up efficiently. It's always going to have dirt and debris and stuff running around in it. The boilers this side can be pressurized. We can put chemicals in via a dosing pot. We can keep this new investment all nice and spanking and clean and running away for plenty of decades. And all we've really got to do is take this plate heat exchanger apart and maintain it whenever it gets clogged up. It's of plate heat exchangers, protects boilers and prolongs life, provides separation from old systems. Trust me, it's much cheaper and easier to replace the plate than the boilers, but if you get a gasketed one, obviously you can maintain that. You can also provide pressure differential between primary and secondary circuits. So if you put boilers in the basement plant room of a building that's 30 stories, you need quite considerable pressure to get that system up and circulating around the top, or you might want to break it at stages as you go up in the building, and you would do that with a plate heat exchanger. So you could keep your primary circuit at bar and a half, 2 bar, and then you could pressurize your secondary side to 6, 8, 10, 15 bar, whatever you needed to do really, and obviously the plate heat exchanger would allow you to do that. And as we've just seen on that schematic, you can keep the secondary side open vented if need be. Downside, you get a single point of failure on multiple boiler applications, which in itself is correct. I disagree with this statement a little bit. If you're maintaining a plate, plates don't generally suddenly fail like something with a motor in it, or electrics or electronics like pumps or solenoid valves and things like that. So if you leave it alone long enough, it will fail. But generally, if you keep an eye on maintaining it, it's a pretty robust bit of kit. Obviously, you've got extra expense and equipment on your project. So if you're pressurizing on both sides of the plates, you need additional pressurization units, expansion vessels, safety valves, dosing pots, all that sort of stuff. A lot of them you need some quite expensive filters to try and keep them clean. A lot of the plate manufacturers will insist on that on the warranty, and obviously there's more kit to maintain. Here's a picture of one that hasn't been maintained, and it's starting to show signs of leaking. That's that really does need stripping down, cleaning up, and gasketing and putting back into service, and needs a bit more love showing to it really. And the other issue with a plate heat exchanger, you've got high system resistance, so your pump needs to overcome, especially on the primary side, it's got to overcome the boiler heat exchanger and the plate heat exchanger. So sizing considerations, you need to think about temperature's going to run at. Nowadays they're getting better and better and better. Some of the cheaper ones, the cheaper the plate really, the larger the temperature drop across the plate. I think some of them are now edging towards 2 and 3 degrees temperature loss, which is pretty good. Usage, the amount of usage, what it's going to be used for, the flow rate that you need through it, the pressure differential, fluid types. So if you're going to be using like antifreeze in the system, such as glycol, whether it's a system that's prone to freezing or a solar system, you need the metals need to be able to handle any sort of aggressive chemical like horrible stuff, glycol, that you might think about running through it. So plate heat exchanger, how are we going to circulate that primary circuit? Exactly the same way as the low loss header. Here we go. Has the boiler got an integral pump? If it has, great. But is the integral pump that's supplied with that boiler, will it overcome the resistance of the boiler? Well, it would. Obviously, the manufacturer wouldn't send it out. But will it also overcome the additional resistance created by the plate? Obviously, it needs checking. Obviously, you can use a primary circuit pump or individual boiler shunt pumps. Again, no right or wrong way of doing that. And as I said, we need to consider the residual head and resistance through both the plate and the boiler. So what size pump do you need for both primary and secondary applications? Seek the manufacturer's assistance. They will spec you a good pump. So that was plates. Let's look at my favourite boiler at Hamworthy. This is called the Hamworthy Varmax, and it's called a no-flow boiler, which is a bit odd because I've been saying through this CPD that modern boilers have to have a fixed flow rate. This does need a flow rate. Obviously, if you don't push any water at all through a boiler, you don't get any heat out of it. So why is it called a no-flow boiler? The official technical stuff on it is it's non-dependent on system circuit flow for safe operation. It's got a pumped internal circulation loop to regulate its own water temperature. It's large water content and it's physically larger than a modular boiler, and it is. It looks like an American fridge freezer, and it's about, the smaller ones are about the size of that and the larger ones are even bigger. It's quite a lump. It's not something that it's going to be carried down spiral staircases or anything like that. You can't take the thing to bits, but it does have its place. So let's have a look at this schematic. Here's our no-flow boiler, no-flow Varmax boiler here, and we've got 4 circuits here. We've got 2 VT circuits, we've got a CT circuit, and we've got a DHW circuit, which will obviously be constant temperature again. We've got all our pressurization equipment over here. We're missing something in the middle here. We're missing hydraulic separation. We've got no header, no plate, no buffer vessel here. Now, if this was a Hamworthy Wessex or a Stratton or most other boiler manufacturers on the market, if you're running the system, and you can connect any other low water content boiler like this, you're better off having a header in it really, but you can do it. So if all these pumps switch off, even if the boiler switches off as well, you've got a lot of residual heat in that heat exchanger. And what happens is if you do not circulate that water for sort of 5 to 10 minutes after the boiler has finished firing on what we call pump overrun, which cools the heat exchanger down, it's going to bang and crash, and it's going to overheat. And after, if you keep doing it, after a while, A, you need to reset the boiler to start it again, which is a nuisance, and B, you're going to damage the boiler after a period of time. However, the Varmax boiler couldn't care less. Let's say this is I don't know, it's a bank. So we got our 4 heating loads in the bank, and let's say everybody goes home at 6 o'clock. So at 6 o'clock, all these pumps and everything can just switch off. And as long as the boiler's got power, it's perfectly happy. It doesn't bang and crash, doesn't overheat. There's 2 reasons for that. It's got a large stainless steel heat exchanger, so it's got a large thermal mass inside the heat exchanger. And over here that you can just about see is a little pump. In our manual, we refer to this as a shunt pump. What it won't do, though, is I prefer to think of it like a D-strap pump, because it won't actually give you any flow out of the boiler. That's not its job. What this boiler's doing, it's monitoring the delta T between flow and return. As the delta T starts to narrow, and as the flow rates start to drop off on your variable speed circuit pumps, what happens is the boiler picks this up and the boiler will modulate. When you get below a certain point, this pump starts to ramp up, starts to modulate upwards. And what happens is it starts to circulate some of its water around its heat exchanger. It's the same way a destratification pump works on a large chlorifier. If you kill the flow rate completely, boiler's quite happy. Obviously it will stop firing, but it will just circulate around this integral loop for a few minutes, and then it will just switch off and it will be happy. So what are the upsides of it? You don't need to install the boiler in a dedicated primary circuit. So believe it or not, although it's a large boiler, it can actually sometimes save you a bit of space, because you haven't got your low loss flow header and your primary pumps and things like that to take into consideration, and it reduces additional equipment. It's good value for money as well, as a stainless steel boiler. Obviously you don't need all this additional kit. All these system pumps can be set for variable speed. Some of them, this one here has got a twin return connection, so it's got a cool return temperature port. So if you've got a like underfloor heating circuits, you would bring the return back from those UFH circuits back into the bottom. You got nice cold return. That's going to induce plenty of condensing inside that heat exchanger, make the boiler even more efficient. Downside is if you've got more than one boiler, because of the large heat exchanger in here, if you've got a system that's fairly modular and you're going to shut one boiler or 3 boilers or whatever off at night, you do need flow isolation through each boiler. Otherwise you're going to be circulating a lot of water through a non-firing heat exchanger. The smaller ones have got about 150 litre water content, so you're going to lose a lot of heat through that. Space limitations, as I said, it's quite a big bit of kit and it's quite heavy. So no flow boiler considerations, your system pumps. So we don't need dedicated primary pumps, we've got system pumps, and what they've got to do is they've got to overcome the resistance of the heating system and the boiler heat exchanger. All the pumps can be set for variable speed. You just think about how you need to control the pump, really. You know, is the BMS going to do it? Is the boiler going to do it? So on and so forth. And that is really the only pumping considerations you need to think about with a no-flow boiler. It's quite a clever bit of kit, really. So that was no-flow boilers. Let's have a look at buffer vessels and thermal store. I think we need to change this. Thermal storage has been developed for, I can tell you now, well over 25 years. It's a technique often known as buffering. Cavemen or cave women, should I say, to be inclusive, use this method. Is a picture of me. I live in the Forest of Dean, and this is me when I go hunting wild boar at the weekend. Only these days I wear my willies because I'm sensitive feet. Seriously, what ancient people used to do was gather up stones. Water retains around 5 times more heat than concrete. So what ancient people used to do was dig a vat of water, a well of water inside their cave or mud hut or whatever they were living in, and they used to leave stones out in the sun, big rocks out in the sun. Probably not so much of that in this country, but in hotter climates. And these rocks used to absorb the heat of the sun, the energy of the sun all day long. And then in the evening when the sun went down and they wanted to warm up their dwelling, they used to take these hot rocks and put them into the vat of water. It would heat the water up, and that water would release that energy 5 times slower than concrete. And it was probably the very first form of central heating. So when you're buffering, when you're including solar heating, it's very, very important that the buffer is big enough to include extra capacity, to include fluctuations in peak demand, and obviously stagnation periods where you've got lots of solar energy hitting those solar panels and it's not being used. So it's very, very important that buffer is there, A, to soak up that energy and also to capture that energy for when you want it later on in the day. Very simple schematic of a buffer. So you've got a heat source, could be anything really, couldn't it? Could be a CHP, air source heat pump, water source heat pump, gas boiler, pellet boiler, oil boiler, anything you like. What we got here is our buffer in the middle. So we got primary flow, primary return, there's a pump on the return there, and we got our system on the go over here. We got a mixing valve here, so it's going to return the water that this doesn't need back into the buffer. Why would you use a buffer tank or a thermal store? Really, it's to either integrate different technologies with each other, such as boilers and heat pumps, or, you know, going back I don't know, 5-10 years, normally you would see them with gas engines, you know, CHPs and boilers. Obviously the gas engine generates heat that it doesn't want. The sensible designer will design a buffer tank, and obviously if, let's say, the heating load is 1,000 kilowatts, but the CHP, while it's generating electricity, can generate 200 kilowatts of latent heat, that's only 800 kilowatts then of heat that you've got to that the boilers have got to produce from that waste heat. Or if you've got a spiky load, so if you've got a district heating scheme, if this is running heating, obviously we're creatures of habit. Most district heating schemes, you get a big energy spike in the morning, everyone gets up ready for work, ready for school, and you get the same thing again in the evenings. Everybody comes home from work and school, and your energy load spikes. So if you've got a nice thermal store of energy ready to go, it will smooth that spike out, and it does exactly the same thing with DHW. So if you've got this might be, I don't know, a school or a sports centre and things like that, where you get energy spikes, or hotels in you know, spikes in energy usage and things like that. With the DHW, again, you could have, instead of having, say, 6 or 7 direct fired water heaters, you could probably cut that down by half, and they could feed a buffer tank or a thermal store, and that would obviously smooth that load out. Just a schematic showing, you know, buffering using thermal storage and renewable energy. So what's happens here on our buffer over here, it's collecting thermal energy all day long, and it's transferred through the core into this buffer. When you want that energy in the evening, sometimes when the sun has gone down, obviously what's going to happen is you've got lots of energy stored in this buffer, and that is ready to go when you need it. Love this statement. So, an upside of buffer vessels is it provides effective buffering. Smooths out your spiky loads, basically. Reduces boiler cycling. Boilers don't like banging on and off too quickly. You can obviously integrate other technologies, as we've already covered, and smooth out spiky heat loads. Downside of it, if you get the boilers wrong, it takes ages to heat the buffer up, or the your water heaters, and the system, you've got to get that buffer up to temperature really when you're ready for your demand. Otherwise, the system isn't going to work because you've got a cold buffer. When you're designing them, you need to think about the hydraulic design. Where are you going to put them on the flow, on the return? You need to think about insulating them. Obviously, you've got one here. If you sort of flatten all the metal out that's made, that's quite a few square meters of material to lose heat out of that buffer. So it's very, very important we try and retain as much heat inside that buffer as we can, make it as efficient as possible. Obviously, it needs to be sized to the temperature and pressure ratings. No point having a 5-bar buffer on a 10-bar system, is it? It's going to get embarrassing. How the system is going to look at that temperature. Larger buffers generally got sort of 4 to 5, 6 BMS sensors down that will take an average temperature reading across the buffer. And that basically that's it for buffering, and that is actually nearly it for the CPD. So what do we cover in part 1? Establishing the existing systems. What are open and closed heating systems? Part 2, what have we covered? Primary circuit design connecting to the secondary circuit. Summary of the CPD. Older systems are generally open vented. When refurbishing, if you could, you should move to a closed and pressurised system. However, if you've got an old building, as we said, stick a plate in. What do you need to consider when reviewing the current system? And what are the methods of connecting new boilers to old systems? We looked at low loss header arrangements, plates, no flow boilers, and buffer vessels. Steve, is everybody getting a feed and outcome sheet? I know we do when we do it as a company.
Yeah.
Okay.
That was excellent, Barry. If you could send me that feed and outcome plus a copy of presentation, I'll send that through to Ella, and then she'll send that out to everyone on the meeting tonight. But that was really good. We got some really interesting questions as well. A few people have left questions and then had to leave, but I don't think it's a problem. There'll also be a copy of this presentation as well on the CIBSE website for everyone to view and review later. So, but if you send me a hard copy plus your feedback forms, I'll send them on, and I'll feedback anyway tonight. For me,
no problem.
Excellent, Barry. But I'll just go ahead with some of the questions.
Yes, please do.
This one is from Tony. It says, your schematic includes a 3-port valve on the secondary circuit. Any considerations required sizing the 3-port valve with the size of the low loss header?
No, generally your 3-port valve will be sized to the diameter of the pipe that it's being fitted to.
Yeah, great stuff. Question from Sarquiz. Hi Barry, is softened water not adequate for topping up the system?
Oh, yeah, it's a bit of a difficult one on that one. Softened water often contains salt, so you need to be very careful with it, and especially the material that the boilers and the system. Yes, you can use softened water. Always seek manufacturer's guidance on that one first, but yes, it can be used. Water hardness is generally controlled with chemicals. Once you get that water in the system, as long as the system isn't leaking and it's not, the pressurization units are not injecting raw water, the chemicals will keep the pH and the system clean. And the basically what an inhibitor does, it takes the undissolved oxygen particles out of the water. It makes the water takes the fizz out of the water, if you like, so it can't oxidize.
Brilliant. Yeah, I've got one from William, who's a designer, and he's had to leave. So he said, we design our boiler circuits as full variable flow and never use low loss headers. We match the flow in the system to the boiler or boilers meeting the demand. This gives us very low return water temperatures for the condensing operation of boilers. Don't know if you've got a comment on that.
If you're doing what I think you're doing, which is varying your flow rate through the boilers, apart from the Varmax boiler, and I think Hove will make one that you can vary the flow rate. Any other boiler out on the market has to have a constant flow rate according to the delta T. Obviously, the wider the delta, the slower the flow rate through the boiler can be. But it's obviously you would reference that to the manufacturer's instructions. The reason boilers don't like having flow rate mess with according to modulation is the boiler is set up to run at a fixed flow rate, and the boiler will then look at the flow and return temperatures. As the delta starts to narrow, what the boiler will do is it will start to modulate. In other words, it will just slow its fan speed down, and that will reduce the modulation firing rate of the burner. If you try and muck about with that with varying flow rates through the boilers, it sort of confuses it. And in our experience, yes, they do work. What you often get is over and undershooting of temperatures, because the boiler, it just confuses the boilers. It's not really the sort of done thing to do.
Yeah. Have you considered compressor pressurization units operating at plus or minus 0.1 bar, protecting old pipework? I think this refers to that schematic where you had the plate heat exchanger and the vented system as part of that, because exactly, you don't want to increase the pressure of your system too much.
No, you can do it that way. It's really down to, I suppose, I think if you've got an old system and you can do a risk assessment on it, in other words, what's going to happen if we do pop a joint? Like I say, I think if you're working in St Paul's Cathedral or the Louvre in Paris or something like that, I think, to me personally as an engineer, I would let sleeping dogs lie. Just leave it as it is, put a plate in. But again, we're coming back to the thing that you lose a bit of energy through a plate, but I think the upside of a plate outweighs the downside of it.
Can you consider using PICVs for a more accurate delta T control across your boiler array?
You can use PIC valves again, but as long as you're maintaining that flow rate.
Right.
So you can use big controllers,
this is another really a statement from William. Can you send me your details of your no flow boiler? And I've got his details here, and I'll send that through to you, Barrie.
Yes, of course. I'll get one of the yes, someone will make contact with you, William, no problem at all.
Great. He said sadly he has to leave for another appointment, but excellent presentation.
Thank you very much. Good to hear.
This is a question from Martin. What plans do you have to meet zero carbon technologies? I think this fits in with another question that the future seems to be heat pumps. How does that affect your, hydraulic designs in the future? Do you think more buffer vessels and?
Yeah, absolutely. We're actually launching heat pumps. Well, we've launched them now. So we've got some heat pumps coming on the market, and then that's portfolio is going to grow and increase. At the moment that we're going up to 70 kilowatts. If a building is modern and it's designed for heat pumps are absolutely fantastic things. Most of them now got a COP of over 4. If you can run a system at 56-degree flow temperature, then you don't need a boiler. Which is absolutely fine with us. We'll sell you a heat pump instead. So we're not going to go skin. Hamworthy, believe it or not, I think it's something like 86% of our work is actually in refurbishment work rather than DMB. So massive amounts of our boilers go into old building stock that we've got in the UK, town halls. Actually, St Paul's Cathedral have got our boilers in it. We've got a really good case study on our website. We saved them a fortune in gas. So heat pumps are not going to be the full-on technology of the future because our buildings are too old. Well, where we see a lot of the Hamworthy sites at the moment moving forwards is going to be in a hybrid system. So the heat pumps will generate 50, 60 degrees flow temperature. That will then be hydraulically designed either through buffers or going into the return of the boilers. So you get, you know, a return temperature of say 50, 60 degrees. The boilers have then only got to create a temperature lift of 10 to 20 degrees to suit the existing system. So hybrid systems for Hamworthy, I think, are probably going to be the way forwards. If you just want heat pumps, we can accommodate with that. And not so far in the future, we're probably going to be running on a mixture of 80-20% hydrogen, which most pre-mixed boilers can cope with without any adjustment. And then in the decades to come, probably we'll be moving on to 100% hydrogen. So I don't think boilers are going to go away. I think they're going to be incorporated with electric technology, heat pumps and things like that. And they're also going to run on alternative fuels.
Great. Do your systems have the ability for BMS to monitor log boiler modulation levels?
Very shortly, we've got a Modbus adaptation coming on, and you'll be able to read tens of parameters off the boiler. So you're definitely flow and return temperatures and modulation rates and things like that. Yes. Yeah.
I've also got another request from Mudassa Ridris. I hope I've correctly spelt that. Can I have how buffer vessel design methodologies? And I'll send that through to you. That's M. Rolt at Silcock Dawson. That's from.
Okay.
Comment from Derek. Great presentation. No mention of degassers and compressor operated pressurization. I think it covered that. Pressurization to maintain low pressures on old systems. What relationship do you have with pressurization manufacturers?
Well, we make our own. We don't do a low pressure version of for older systems, but we make our own range of pressurization units.
Yeah, and what one from Garfield. Barry, can you send me this presentation link on this topic because I'm hearing impaired? Yeah, I don't think that's a problem at all. That's great. That'll get sent through. Not all and air dirt separators are efficient. What criteria do you offer your customers to choose the correct unit? From Derek.
Not all air and dirt separators are efficient. Efficient. I'm not quite sure I understand that question. Efficient in removing the air and dirt.
Yeah.
Okay. Yeah. I mean, we do the you know, the general mechanical ones. Obviously, there are other companies out there, Spirotech and people like that, do all sorts of complex air and dirt degassing systems and things like that. But as a company, we only do a basic air and dirt separator that just goes up with pipe sizing.
Yeah, brilliant. Well, Barry, that's the end of the questions. Hang on, we've got another one just come in. You mentioned about running 80 to 20% system on hydrogen. What about the rest? Would it be provided by heat pump or other type of boiler?
No, I think you misunderstood what I said. So gas boilers in the future will probably, I mean, there's quite a few schemes now doing it as a test. So what the plan is in the future is to decarbonize the gas grid. So it's going to start off with a 80% methane, 20% hydrogen mix in the line. Then as the infrastructure moves on, and this is a few decades away, we're going to probably move on to hydrogen. Obviously, that's got its own challenges. It's got a natural gas flammability rate is 5 to 15% for methane. Hydrogen is something along the lines of, I think, don't quote me on this, I think it's something like 2 to 90 odd percent flammability levels. But it's strangely enough slightly more difficult to actually create an explosion because it leaches out through the walls of copper and concrete and all sorts of bits and pieces. Funny fuel. So yeah, in the few decades time, I think it's going to be a mixture of heat pumps and hydrogen. what's going to happen with the hydrogen, it's only carbon neutral, because you need a lot of electricity to create hydrogen. So unless it's created by renewable sources, solar and wind and wave and tidal and so on, if you're generating that electricity from a coal-fired power station or a nuclear power station, you haven't decarbonised the grid. You've just changed the fuel.
Brilliant. Question from Mark: will you be producing hydrogen kits for your existing boilers, or will there be new products? As you know, carbon is a concern for clients.
Absolutely, yep, and we recognise that. I'd just like to explain the process of governmental thinking at the moment, or not, lack of. Hamworthy, as I said, we're owned by Group Atlantic, so I think we're probably one of the, if not the biggest group of boiler manufacturers in the world. You would think that someone within government might want to come and have a little chat with us, because this is what we do. We produce this heating equipment. No. Our R&D departments and our product management teams and stuff have got the unenviable task of second guessing what the government initiatives are. So at the moment, Boris Johnson is showing off at the various different climate meetings, with various different heads of states, and he's promising carbon neutral and so on and so forth. We have no idea what's going to happen if the Conservative government gets voted out and someone gets voted in. It's a difficult thing to follow. So on that, there obviously has to be a commercial reason for us to develop things. So at the moment, you don't need any form of conversion kit whatsoever to run on an 80-20% hydrogen mix with any of our products. You just basically connect it up and commission it. You wouldn't notice the difference. You would notice a slight drop in output, because hydrogen has a slightly less calorific value than methane. So you would need to maybe adjust your sizing criteria accordingly. Aside that, there wouldn't be any difference. Moving forwards, then what will happen is the equipment will still be sold at an 80-20 mix, but then there will be a commercially available conversion kit for when the area that you live in, or this equipment is installed in, moves over to 100% hydrogen, and then moving on from then, all boilers will basically just run and be sold and run on hydrogen gas.
Yeah,
that's quite a way in the future. Right.
Thank you, Barrie. Just a thank you from Max, a thank you from Spiros.
A pleasure.
In particular, from Rot. I really like the answer about hybrid solutions of heat pumps with boilers. No wonder heat pump COPs reduce drastically during winter periods. So thanks. Excellent answer.
We've got some new ones coming out with propane that will give a higher, a few years time, but it will give a higher flow temperature.
Yeah, again, Sarquis, good presentation. Thank you for response. And I think we'll invite you back for part 2 and renewables as well, Barrie. That will be very good, with heat pumps and the mix and the hybrids and how that changes hydraulic circuits. I think that would be, really, it's well attended this evening, but also I think people look forward to that as well too. And again, Noel says thanks for the presentation, and home county southeast. So great. Well, I think we'll wind it up there, because you've spoken for quite some time, Barrie, and it's been an excellent presentation, and people are just dropping in thank yous all the way through. So if you'd like to send me across the slides for that and your feedback form, I'll send that through to Ella, who'll send that forward. But the presentation itself, tonight's presentation, recorded presentation, will be on the CIBSE website, and everyone can connect and view it on them. But again, Barrie, brilliant. Have a good evening, and yeah, enjoy a glass of wine. You know, I think you thoroughly deserve it tonight.
Thank you very much. So thank you everybody for listening. I'm glad you enjoyed it.
Yeah, they did. Yeah, there's lots of thanks coming through. Unfortunately, we can't hear it and clap, but you know, they're definitely there from everyone who's attended. Brilliant. Again,
My pleasure.